Hello and welcome back to my Physics Online Video Lecture Supplement series. In today's lecture, I'm going to discuss a little bit about uniform circular motion, and specifically I want to look at the topic of rotational kinematics. So this is all about trying to describe the motion of an object which is undergoing a rotation, a revolution, an orbit, as opposed to translational kinematics, which we looked at in an earlier lecture, lecture 2 and lecture 4 actually, in which the object is translating from one point to another. In other words, moving from point A across the room to point B. So in today's lecture, we're looking at rotational kinematics, in which an object is actually moving from point A to point B around some orbit. So point A might be here, point B is here. And what we're concerned with is many of the same terms. There's still a position, a velocity, and an acceleration that can be defined for rotational motion. The trick is that we're concerned more with angles than distances. So in moving, say, from this point here to this point here, the little seat on the Ferris wheel has actually moved through, yes, some distance, but also because it is moving about in a circular motion, it's easier to define this guy's motion in terms of an angle. In particular, because this point, this little crossbar here on the Ferris wheel support struts, has also moved through that same angle. So the simplest case of rotational kinematics would be uniform circular motion, and of course this Ferris wheel is an example of that. And we can in fact combine rotational motion with translational motion. For example, if you have a wheel which is rolling, a car moves because the wheels turn, and so the car is translating. The wheels are also rotating and translating. How do we combine those two motions? So as I hinted at before, we still have terms such as position, velocity, and acceleration when we're talking about rotation, just like when we were talking about translation. The difference is that in translation, we just simply said position, which we used either an X or an R. We had velocity, which was V, basically how is your position changing per unit time, and acceleration, how is your velocity changing per unit time. In rotational motion, we look at how the angles are changing. So we use a theta to talk about the actual angular position. Where on the circle are you, basically. Angular velocity is omega, is how is the position changing per unit time. Notice that the units are actually radians here. You can also get an angular frequency, which is a sort of angular velocity that is defined in terms of how many complete rotations do you make per second. So an alternative unit might be revolutions per second or cycles per second. And then there's angular acceleration, which is the change in angular velocity per unit time. And again, the preferred unit is radians per second squared. And these angular terms that we have here are actually quite analogous to the translational terms that we have over here. So angular position really is analogous to position. Angular velocity really is an analog to velocity. Angular acceleration really is an analog to translational acceleration. Specifically, you can show that the equations that govern all of these things are basically going to end up being the same. The definitions are the same. The equations that govern them are going to be the same. So position, we used an x or an r. The displacement, we used a delta x or delta r, and is just final minus initial. The same is true with the rotational terms. Velocity, the average velocity was change in position per unit time, or displacement divided by time. And again, you could get an instantaneous velocity by taking the limit as this time goes to very small time, for example, to 0. And for angular velocity, there's a very similar definition. It's the angular displacement per unit time. And with acceleration, you have the change in velocity per unit time. With angular acceleration, for the average, you have a change in angular velocity per unit time. What this leads to is that if you are using constant acceleration, you get very similar equations for your rotational motion as for your translational motion. So your position in translation was basically 1/2 times the acceleration times the time squared plus the initial velocity times the time plus the initial position. And notice over here that the angular position is 1/2 of the angular acceleration times the time squared plus the initial angular velocity times time plus the initial angular position. So notice that not only do these equations have the same general form, 1/2 of something t squared plus something t plus something else, but in fact each term is analogous to this equation over here. So the initial angular position corresponds to this initial position here. The initial angular velocity corresponds to this translational initial velocity here, and so on. Ditto for finding the velocity as a function of time and for the angular velocity as a function of time, and ditto for this time-free equation, which relates final and initial speeds to the acceleration and the distance traveled. Here it's the final angular speed squared minus the initial angular speed squared is twice the angular acceleration times the angular distance traveled. So I wanted to go ahead and work a few short examples here just to make sure that you're following. And so let's go ahead and start with this example that has a merry-go-round that's rotating at some constant rate. And we know that it's going to complete 5 revolutions in 4 seconds. So our question is, what is the angular speed? So to represent angular speed, we can use this little omega, and it's defined as change in angular position or angular displacement per unit time. In other words, the angle through which the merry-go-round has rotated divided by the time that takes. So we're given that it completes 5.0 revolutions in 4.00 seconds. But remember that what we want here is an angular speed in radians per second. So we need to multiply this revolutions times the fact that there are 2 pi radians in 1 revolution. That's how the radian is defined. If you haven't used a unit circle for a while, you might want to go back and review unit circles at this point. So what we do here is we basically can do our little multiplication and our little division. So we have 5 times 2 pi. There's pi. And then that's going to be divided by 4. And we get 7.85 radians per second. So this is approximately 7.85 radians per second. All right, our second question here is, if the above merry-go-round is accelerated for 3 seconds, and after that it completes in 3 seconds a total of 7.5 revolutions, what was the angular acceleration? All right, so we're using the above merry-go-rounds. That was the previous examples, and of course we got 7.85 radians per second for that previous example. And therefore we can use that the angular acceleration is always going to be difference in angular speed per unit time. So that means that the final minus the initial angular speeds divided by the time is what we need. So at this point, what we need to find is what is this final angular speed. So to do that, we use the fact that it completed 7.50 revolutions and that it did this in 3.00 seconds. So this is revolutions per second, and since this needs to be in radians, we've got to multiply by our 2 pi worth of radians per revolution. So if we do that, what we get is 7.5 times 2 pi, and that's going to be divided by 3. You get 15.71. So the final angular speed is about 15.71 radians per second. Okay, now we can find this average angular acceleration. So we just found that the final is 15.71 radians per second. We found in the previous problem that the initial is 7.85 radians per second. So we're going to divide that by the time that it was accelerated for. It's accelerated for 3 seconds, so 3.00 seconds. So that means that the angular acceleration is, let's pull up our calculator, this was the final one, so let's take away the initial one, 7.85, and then we're going to divide that by 3. And so you get 2.62, basically. So alpha is 2.62 radians per second squared. All right, so those are 2 relatively short examples. Let's do a slightly longer example just to be safe. And the slightly longer example, we have a merry-go-round which is initially at rest. It's given some angular acceleration of 3 radians per second squared until it reaches its final angular speed of 15 radians per second. The question is, how much time does this acceleration process take, and what is the total displacement, total angular displacement during this time? All right, so the first thing that we want to do is solve for the amount of time that this is going to take, because that's the first question that we're asking. How much time does this acceleration process take? Okay, so we're going to label that delta t. And we're given that the average angular acceleration is 3.00 radians per second squared. We're given that the final angular speed is 15.0 radians per second. And we're told that this thing is initially at rest. So this is telling us that omega naught is 0 radians per second. All right, so in general, the average angular acceleration is defined as the change in angular speed divided by the time. So that means that we can rearrange to solve for this time by basically solving this equation for time. So that's going to be delta omega over alpha. So delta omega, of course, is going to be the final minus the initial divided by this acceleration. So what we have, therefore, is that the time that it takes is going to be 15.0 radians per second minus 0 radians per second over 3.00 seconds. So that's pretty straightforward. This should give us 5.00 radians per second. 5.00 seconds. This should be radians per second squared. There we go. Okay, so now we have how much time it takes, and basically we're going to rewrite that as time in our next equation, which the next equation basically says that the final angular position should be 1/2 times the angular acceleration times time squared plus the initial angular speed times time plus the initial angular position. So if we want to find out how what is the total angular displacement, we could label that as delta theta, and that of course is theta final minus theta initial. So if we subtract the theta initial from both sides, then we have that delta theta is 1/2 times 3.00 radians per second squared times, since we're using this time here, 5.00 seconds, quantity squared, and then this one right here actually was 0 initially. So our change in angular position, or the angular displacement, therefore is going to be given by 1/2 times 3 times 5 squared is 25. So that's 37.5 radians. So in this 5 seconds during which the acceleration is occurring, you get 37.5 radians of total angular displacement. So we have now solved this relatively long example. I should here add one further note about these angles, about the direction involved in angular quantities, which is that there's basically two ways of defining direction here. One is the sort of intuitive way, which is to define all these directions for the angular positions as being either clockwise or counterclockwise. The other is, well, really the other one is by using what's called the right-hand rule. And the way that the right-hand rule works is, in terms of these angles, is imagine that you take your right hand and you point towards, let's say we want to figure out what is the angular displacement. So imagine that you start with your right hand, your palm is in sort of the center of the circle facing perpendicular to the circle, and your fingers therefore are pointing to the initial angular position. Now curl your fingers so that they point around towards the final position, and the direction in which your thumb is pointing is the actual direction of the angular displacement. And this works also for angular velocity and for angular acceleration. Basically, the same trick will work exactly for angular velocity. For angular acceleration, you do the same thing, but we talk about which direction was the initial velocity in and where's the final velocity in. So this will become sort of more important later when we get into torques and when we get into angular momentum. For right now, we can just think of everything as clockwise or counterclockwise if you'd like, and bearing in mind that you can use the thumb of your right hand to find a simple vector that is, let's say the circle is within x and y, then that simple vector that gives the change in displacement can be defined as either a positive z or a negative z direction. All right, earlier on in this video, in this lecture, I kind of suggested that it would be useful to review the unit circle. We can actually define the units involved, the unit of radians, by using a circle sort of like this. And basically, the way that you define your radian in general is that you take the arc length that you've traveled in going through that angle theta, and you divide by the radius of the circle. So for a unit circle, the radius is always 1, and so this arc length simply becomes the number in radians once you've divided out the unit of 1 meter or whatever. And so 1 radian is actually approximately equal to 57.3 degrees of angle. And the way that you can do an actual conversion is that there's 360 degrees in a complete circle, and the circumference of a complete circle is 2 pi r. So the arc length of that complete circle would end up also being the circumference. And so if you divide that circumference 2 pi r divided by r, you end up with 2 pi radians. So there's 2 pi radians in a whole circle, there's 360 degrees in a whole circle. One implication of this, by the way, is that you can now link rotation and translation for a rigid rolling object. And basically, here's the process for relating rotation and translation. The total circumference is always going to be 2 pi times the radius, 2 pi r. So if we want a fraction of that circle, you can basically use the arc length, L equals S equals theta times r. And this arc length basically is if you stuck, say, maybe this circle is a wheel and there's a piece of gum stuck on part of the wheel. As the wheel is rolling, after it rolls through some given angle, how far will that piece of gum have actually traveled? What's the distance that's equivalent to this arc length? Well, if this object is actually rolling and rolling without slipping, then as this wheel sort of rotates around like this, it's also going to be translating from here to here because it is rolling. And so it's basically rolling, 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 rolling. And the distance that it's going to translate is going to be actually equal to what this arc length is that you've traveled through. So the distance x is equal to the arc length, and theta is equal to both s over r, the arc length over r, and x over r, where x is the distance that's been traveled. Okay, so if you have a rigid object which is rolling without slipping, then you get a translational distance x equals s, which was defined as in the previous slide, but that also means that you can convert from angular speed into translational speed, and you can convert from angular acceleration into translational acceleration. And the reason why that works is if you wanted to find the angular speed, the average angular speed, for example, you take a delta theta over a delta t. All right, so if we're going to take delta theta over delta t, that's like dividing both of these over delta t. So this right here then becomes basically delta of x over r divided by delta t. And r is the radius of your wheel, so r is not really changing. So this right here can become 1 over r times delta x over delta t. But delta x over delta t, by definition, is the average of the translational speed. So that means that we've just shown that the average rotational speed is the average translational speed over r for an object that rolls without slipping. Okay, well, if these averages are true, the only other step is to basically take a limit as this time gets very small to get the actual instantaneous values, and the result is basically that both of these averages get dropped, and you can write that the angular speed is the translational speed divided by the radius. And this same process works again if we want to show for the average angular acceleration. So average angular acceleration, of course, is change in the angular speed per unit time. We just showed that the angular speed is v over r. So this becomes delta of v over r divided by delta t. Once again, r is a constant. So once again, we end up with 1 over r times delta v over delta t. And so that implies that the average angular acceleration is, since this right here is the average translational acceleration, the average angular acceleration will become average translational acceleration over r. And again, that also means that the instantaneous angular acceleration is the instantaneous acceleration over r. So that's how you get these relationships. It's worth noting here that for all of these directions, angular position and angular acceleration, angular velocity, the way that you figure out whether it should count as a positive or negative is that counterclockwise is usually positive and clockwise is usually negative. And again, that goes back to that right-hand rule that I described. Imagine setting a clock face up and then putting your hand on the clock. Now wrap your fingers so that they are going counterclockwise and see what direction your thumb is pointing in. It should be pointing straight up. So counterclockwise corresponds to positive because by the right-hand rule, your right thumb will be pointing up, and that's the positive z direction. If you wanted to wrap your fingers clockwise, you have to actually turn your hand upside down so that your thumb is pointing downward. And so clockwise with the right-hand rule would correspond to negative z. And so that's why clockwise is negative. Similarly, if you have an object which is translating with a positive velocity, as we usually define it by looking at the object and seeing is it moving from left to right or right to left, then the only way to get that to happen is for the object to be, if it's rolling without slipping or if it's rolling in general, chances are that it's rolling in a clockwise direction. So that means that a positive translation is paired with a negative rotation and vice versa. All right. So there's another concept which can be tied into all of this, which is called tangential motion. And the equations which we've described so far can relate rotation to translation, but they can also relate rotation to tangential quantities. Tangential quantities basically mean imagine that piece of gum again that was on the wheel. So here's your piece of gum. The wheel is rotating around like this. Maybe the wheel is rotating in place, for example. So if the gum is right here and the wheel is rotating this way, then instantaneously the gum would need to have a velocity in this direction. So again, you've got your piece of gum. The wheel is rotating around like this. This piece of gum that's stuck at point P at a particular instant must be moving in this direction. And notice that this direction is actually tangent to the circle. If the piece of gum were right here, then it would need to be moving in this direction. Again, this is tangent to the circle. So this piece of gum actually is undergoing what's called tangential motion as well as rotational motion. And as you can see, the tangential quantities I've labeled with a little subscript t. So the tangential speed is the radius of the wheel times the angular frequency. The tangential acceleration is the radius of the wheel times the angular acceleration. And you can get an application of this in these motions that involve rolling without slipping. So if you have a bicycle that moves a distance delta x when its tires rotate for an angle of delta theta, then the tires, if they were to be spun in place, would have a speed of omega, and the vehicle itself would have a speed that's equivalent to these tangential speeds above. And the greater the change in rotational rate, the more the vehicle is going to speed up or slow down. With that said, there's a little bit more to tangential velocity and tangential speed to tangential acceleration than what I have mentioned here. And I'll come back to that point in a little bit. All right, so if you have a car that is rolling without slipping, then it will have a speed that is given by the radius of the wheel times the angular rotation. So as an example, let's say that we have a car whose tires have a 25 centimeter radius. We want the car to have a speed of 25 meters per second. That's getting close to about 60 miles per hour. So what's the angular speed that you're going to need for these tires to have, assuming that it's rolling without slipping, if you're going to have this speed? All right, well, the way that we solve this is that so far we have omega equals v over r, and that means that, so we have omega equals v was 25 meters per second, r was 25 centimeters, so 25 centimeters means the same thing as 0.25 meters. So we're going to divide this by 0.25 meters, and so that should be 100 radians per second. I would be remiss here if I did not mention that there is a little bit more to the tangential speed than what I lit on. The description I've used so far has kind of divorced the rotational motion from the translational motion, other than that I just used it to calculate what the speed would be based on the angular speed, or vice versa. The reason why I say that there's a little bit of a divorce going on is to be explained as follows. Imagine, first of all, that you have this car. So it's moving forward at some speed v. Now imagine, if you will, that you have your piece of gum on the bottom of the tire right here. So if I were to have lifted the car off the ground so that this wheel is spinning at 100 revolutions per second, or 100 radians per second, or whatever, then your expected tangential velocity would be like this. But the thing is that the car is actually moving forward. So that means that this tangential velocity, the actual velocity of this little dot that's sitting here on the car, is going to have to be given by this tangential velocity plus the actual translational velocity. So we could call that V tan and V tran, if you will. So V total is going to be V tangential plus V translational. So if you happen to be here at the bottom of the car's motion, these two are going in exactly the opposite directions, they will tend to subtract from each other entirely. If you're here at the top of the car's motion, then this tangential velocity is actually going in the same way as the translational velocity. And it turns out that, for example, this right here, this tangential velocity has to be r times omega. Okay, we already established that on a previous slide. So what you'd end up with is for the bottom, so for the bottom of the car, you would have that the total speed of this would look like r times omega, and this is from the translation. So this is the translation minus r omega from the tangential. Okay, and same r omega, that means that this thing has a speed of 0 with respect to the ground. The one at the top, incidentally, V total, is going to be r omega from the translation plus r omega from the tangential. Looks like 2r omega. So this point on the tire is actually instantaneously moving twice as fast as the car is, and this point on the very bottom is actually stationary instantaneously with respect to the ground. That's a very important point, because if the tire is stationary with respect to the ground at the point of contact with the ground, that implies that the type of friction that this tire is using to basically propel the car forward, or alternatively if you're braking, the type that's used to brake, is not kinetic friction, but rather static friction. And suddenly it makes sense why anti-lock brakes are such a big deal. Because if the brakes lock, the tire starts skidding, it's no longer rolling without slipping. That means that this thing right here is moving forward usually at a greater rate than would be warranted just by the wheel's rotation. That means that this is no longer stationary with respect to the ground, which means that the amount of friction to resist the car's motion is lessened, and so suddenly you're braking and you're not getting as much deceleration as when you're rolling without slipping, or in other words, when you're not skidding. So that's why you need anti-lock brakes on your car, or that's why skidding is such a bad deal. Okay, so now I want to return to the simple rotation about a circle. Simple motion in which we're only rotating around the circle. We're not rolling, it's just like a merry-go-round or a bike wheel that's spun but held so that it's not translating. So that means that the motion is that a particle stuck here on the wheel is going to move from here to here and from here to here and so on, and is not moving off this way or this way as this motion goes on. And what's so important about that is if you take a non-rigid object, For example, you could have a planetary orbit is not a rigid object. A ball that's on a string that you're swinging overhead, or a tether ball, for example, is not really a rigid object. Then the object which is undergoing this rotation can get closer to the center, or it can move farther away from the center. So here's the center. This object, if it's not rigid, might move in, say, an ellipse. So it gets closer and farther and closer and farther. It could be a ball on a string, in which case it kind of spirals in like this as the string is getting shorter. Okay, but if you have a rigid object, and that rigid object has a constant angular velocity, then the actual tangential velocity has a constant speed but a changing direction. So you can see that in this diagram. Here is the tangential velocity at point B. Here is the tangential velocity at point C. And as you can see here, this length of the vector is the same in both cases, but the direction has changed. So if that's true, that means that the velocity vector has undergone some change. That means that there is a delta V. That means that since this has happened in some amount of time, that there must be some acceleration going on for this particle, because it has changed its velocity from here to here. So it underwent some sort of acceleration. We call that type of acceleration centripetal acceleration. Right? A change in velocity implies acceleration even if the object isn't speeding up or slowing down. And in this case, the change in velocity, and hence the acceleration, actually points towards the center of the circle everywhere. So you can get that by sort of drawing your initial velocity vector up here and your final velocity vector up here, as shown in this diagram. Your initial velocity vector is this way, your final is this way. So your final would be here. The acceleration points towards the center. And that's true everywhere on this circle. The only way to get from this to this while staying on the circle is to have a center-seeking acceleration. The center-seeking, another word for that is centripetal. And if you have uniform circular motion, then that acceleration can be found by taking what this speed is, squaring it, and then dividing by the radius. So the centripetal acceleration is v squared over r, which is also equal to r times omega squared, because v squared, recall, is r times omega quantity squared. So you have r squared omega squared over r. So that's r omega squared. And now let's allow this thing to start moving again in a translational direction as well. So you have your rotational motion, and the acceleration for that might be given just by the centripetal acceleration. If you start spinning this thing up, let's say that it's still being held by like a spoke at point A and is not being allowed to translate, you just start spinning the circle up, or you spin the wheel up, or whatever this thing is, then you have a centripetal acceleration because it is still going around the circle. You also have to have a tangential acceleration because this is either getting faster or slower. And if you then throw in rolling without slipping, you might also have a translational component to that acceleration, which you can again get from the previous sets of equations that relate the rotational acceleration to the translational acceleration. So let's look at a couple more short examples to help us out here. So you have a merry-go-round again, and now we know what the radius is. It's 3 meters from the middle to the edge. And you've got an angular speed of 2 radians per second. So the question is, what's the tangential speed of a passenger who's sitting out here on the edge of the merry-go-round? Okay, so we have that the tangential speed v sub t is going to be equal to the basically the rotational speed times the radius. So that means that we have 2.0 radians per second times 3.0 meters. And so the tangential speed is going to look like 6.0 meters per second. So a person who is riding on the edge of that merry-go-round will have a tangential speed of 6 meters per second. And if they were to step off of the merry-go-round while spinning, they would be moving tangentially to the merry-go-round at 6.0 meters per second. So they end up displaced somewhat from the edge of the merry-go-round, depending on how much time the falling off the merry-go-round actually takes. All right, the other question is, for this same merry-go-round, what is the centripetal acceleration of the passenger, and what changes if the passenger moves 1 meter towards the center? All right, so the centripetal acceleration, a sub c, you can get from v squared over r, in which case you'd put in 6.0 meters per second. You'd square that, you'd divide by 3.0 meters. So this is 36 meters squared per second squared divided by 3 meters. So this is 12.0 meters per second squared. So he's actually pulling an acceleration that's a little over 20% higher than gravity as a centripetal acceleration. We could also solve it a second way, which is to put the centripetal acceleration as r times omega squared. So that would be 3.0 meters times 2.0 radians per second squared. So this obviously is 4 times 3, and so again you get 12.0. Actually, if we're keeping track of significant figures, it's just 12 meters per second squared. Still about 20% higher than gravity. Okay, the other question though is, what is going to change if this guy moves 1 meter towards the center? And there's a little bit of context that we would need for this. The thing is that if he moves towards the center, he's actually going to cause the merry-go-round to change its speed. And that ties into the topic of the conservation of angular momentum, which we'll get to later. But I think a better way of saying this question is, suppose he moves 1 meter towards the center and all else is sort of kept equal. In other words, the merry-go-round is either spun up or spun down as necessary to either give him the same tangential speed or the same angular speed as he had before. So let's just take the case where he retains this angular speed of 2.0 radians per second, and he moves in to 2.0 meters. If that's the case, then the centripetal acceleration should be 2.0 meters times 2.0 radians per second squared, and so that's going to be 8 meters per second squared. Okay. On the other hand, suppose that he moves to the center and the thing is spun up to keep him at a speed of 12 meters, a speed of 6 meters per second. So if instead we have v tangential is 6.0 meters per second and r is 2.0 meters, then what's going to happen is that the centripetal acceleration will be 6.0 meters per second, quantity squared divided by 2.0 meters, which is 18 meters per second squared. So you can see that it depends a lot on what it is that we're keeping constant. And again, in the context of conservation of angular momentum, neither one of those things would necessarily be constant. As the passenger walks towards the center of the merry-go-round should actually speed up on its own so that a quantity called angular momentum is conserved. And we'll get into that in a future lecture. We actually don't have enough information in this problem to determine exactly how much it would speed up. It turns out we need to know some more information about the merry-go-round and the passenger and what their masses are and what the distribution of the merry-go-round is and so on. So I wanted to basically do a little roundup of the concepts that we've learned in this lecture. The first one is tangential velocity, and the tangential velocity is the component of the velocity which is tangent to the curve along which an object is rotating, so as per this diagram. And it will be the instantaneous velocity of an object undergoing uniform circular motion about a fixed axis, in other words, rotating but not translating. The speed in the case of that type of motion, rotation with no translation, the speed will be constant so long as the object rotates with constant angular velocity, but the direction is changing at a constant rate, and so that you end up with a centripetal or center-seeking acceleration. If you have a rigid body, then each part of the object is going to be fixed in position relative to all the other parts. That's what it means to be rigid. If rotating, what that means is that each point on the body is going to undergo circular motion about the axes of rotation, and all parts are going to rotate through the same angle in the same amount of time, so that every part will basically have the same angular displacement in a given amount of time, and therefore they will all have the same angular velocity. And if they all have the same angular velocity at all points in time, then they must also have the same change in angular velocity, so they will all have the same angular acceleration. So in a rigid body, everything basically has the same angular displacement, angular velocity, and angular acceleration. Basically everything is moving together. Finally, we talked a little bit about rolling without slipping, which, by the way, is sometimes called a pure rolling motion. And if you have a cylindrical, or for that matter, spherical object, you can get rolling without slipping reasonably easily, as long as you're not doing something crazy like, rolling it down a very, very steep ramp. And basically, a point on the edge of the object is going to move through a given path length s that is going to be actually equal to the object's translational distance delta x. And it's modeled kinematically as a combination of pure rotation and translation. We talked about that in the context of the velocity of an object at some point on this circle that's moving, having a combination of the tangential and translational velocities. You usually need some sort of static friction, sometimes called rolling friction, in order to have this occur. And as a result of this total velocity being the tangential plus translational velocity, not all points will have the same total velocity. In fact, every point will have a different total velocity because every point has a slightly different tangential velocity thanks to the direction being different at each point. So I wanted to throw up a few questions that you could ponder, and I'll do this in the context of a bicycle. And let's suppose that the bicycle rolls without slipping. So the translational speed of the bicycle is going to be constant, 10.0 meters per second. You've got a given diameter for the bicycle tire. So here's a few questions that you could try to answer at home. What's the bicycle's rotational speed going to be? What's the total speed of the point on the tire which is in contact with the ground, with respect to the ground? That's kind of a conceptual quiz. If you've been paying attention, you should have the answer right now. What will be the total speed of a pebble as it passes through the top of the tire's motion? Again, that's kind of a conceptual question. What's the acceleration of the rider? That's a simple conceptual question. And what's the acceleration of a pebble on the tire? So you should think through what these questions are. Some of them are very conceptual and easy. Some of them maybe are a little bit more difficult. They should all be fairly straightforward. And that's actually it for part 1 of this set of lectures. So I should always try to give credit where credit's due by giving a list of the references that are telling where I got all these diagrams from. Some of them maybe I made myself, but a number of them I pulled from sources like Giancolli or Cengage's textbooks or the OpenStax text, etc. So thanks for watching this video, and I hope you find it helpful. So long for now.